Hey everyone, welcome to Organic Chemistry. In Chapter 1, we are going to go through a little bit of a review from the important concepts that we learned in general chemistry that will be the most important things to carry forward when studying organic chemistry this semester. So today we're going to go through some things that you usually talked about in Gen Chem 1, such as electron configurations and orbitals, and bonding. So a lot of just those basic concepts that I want to remind you all about and make sure that everyone kind of jogs their memory on before we get started with new organic chemistry stuff in this class. So you might be wondering, what is the difference between inorganic chemistry and organic chemistry? And essentially we could break it up into two different classes, where inorganic compounds are usually non-living, and those are composed of our minerals and gases. And organic compounds are often seen as living, and those are our plants and animals. Now, when we're specifying organic chemistry, really what we mean though is chemistry of carbon-containing molecules. So carbon is really the major backbone of organic chemistry. It's definitely the most important element on the periodic table this year. So we are going to look at a ton of different carbon-containing molecules and how we name them, the types of reactions that they undergo, and their structure and properties. So those are honestly the three major classes that we'll look at for all different types of groups of molecules. So nomenclature, which is just the fancy name for naming, the structure of the different types of molecules we'll look at, and like the different properties that they have, such as boiling point or melting point. And then later on in the class, after we kind of get some of the basics down, we will start learning something known as chemical mechanisms. And mechanisms are a super important part of studying organic chemistry. Basically, a mechanism describes how you go from reactants to products, and it shows all of the intermediate steps in between. And so in order to learn mechanisms, you have to really understand organic molecules and understand a lot of the basics that we're going to recover in this first chapter. So the questions we'll ask ourselves is, what happens to a molecule during a reaction? Why does it react the way it does? And why do chemical reactions even occur? Our major thing when we're learning mechanism is that we're going to follow the electrons in a reaction. Electrons are the most important thing to be able to track and follow and, understand where they start and where they end when learning chemical mechanisms. So all of that will come with time. On the right-hand side, we just have a few examples of three different organic molecules, just random ones to kind of look at to get you started here. D-glucose. Glucose is blood sugar, and essentially that is a simple monosaccharide, and so it's mainly made by plants during photosynthesis from water and CO2, using energy in order to produce that. Next to our glucose, we have acetaminophen. Acetaminophen is the active ingredient in Tylenol, and so this is a pain reliever or a fever reducer. And there's certain things when we look at these molecules that we can identify, and we'll learn about all of them individually. But for example, in acetaminophen, we have something called the benzene ring. That's a specific grouping of atoms. We have an amine group, which is that nitrogen-containing group. In our glucose molecule, we have something called a cyclohexanol ring. So that arrangement of those 6 carbon atoms forms that specific shape that you see, and that's something we'll definitely talk about. And lastly, on the bottom here, we have oleic acid, which oleic acid looks like a very long, big, mean molecule, but it's just a fatty acid. And so you may have heard of a monounsaturated fatty acids before. This is called a monounsaturated one because mono for one. It has one double bond in its carbon-hydrogen chain, which has 1 degree of unsaturation right there. So that's where that name kind of comes from. And this is in various animal and vegetable fats and oils. So if you've ever heard of omega-3, omega-6, omega-9 fatty acids, this would be an example of an omega-9 fatty acid. So these are just some examples of kind of analyzing just the basic structures and functional groups and things in organic compounds. And this is going to just be all the types of stuff that we look at this semester. So next we want to review some theories of chemical bonding, and the two major types of chemical bonds are ionic bonds and covalent bonds. Covalent bonding will definitely be the most important to us in organic chemistry because we're dealing with carbon, and carbon is a nonmetal, which that is what is involved in covalent bonding. But just to compare both of them, we'll kind of go through a rehashing of them a little bit. So it's important to be able to determine how many valence electrons a specific atom has, what valence shell those electrons live in, and how we did that is we wrote electron configurations. So looking at the periodic table, we could quickly determine what the electron configuration of something was. So let's practice writing it for magnesium. We would start in period 1, column 1. So we would say we would have 1s1, and then over here we would have had at helium 1s2, and then those two first electrons would have filled our 1s orbital. So we can write down 1s2, and then moving to period number 2 now, so row 2, lithium and beryllium would fill 2s2, and then moving all the way over to boron, we would have 2p1 all the way through neon, which is 2p6. And then now our P subshell is full, so we would have to move to period number 3, starting with sodium, and that would give us 3s1, and then 3s2 for magnesium, so 3s2 here. So that's how we write out the longhand notation for our electron configuration. We also could write a shorthand notation. So our shorthand notation was where we looked at the preceding noble gas that came before. So the preceding noble gas before magnesium is neon, so we would write that noble gas in brackets, so neon brackets brackets, and then essentially the electron configuration that comes after that. So after neon we have 3s2. And that's a really quick, easy way to see what your valence electrons actually are and what your outermost shell is. So our valence shell in this case is the 3s, because that's our highest value of N, which is 3. And those electrons that live in that valence shell are our valence electrons. So we have 2 of them in the case of magnesium. And so all the other electrons that are in the 1s all the way through the 2p, those are often referred to as our core electrons. They're not involved in any type of ionic bonding usually because they are tucked away closer to the nucleus, whereas the electrons in the 3s2 orbital are the furthest away, and so they're the easiest to remove from and form an ion. They're the easiest to remove from a metal to form an ion. We also can look at the tile, the element tile, in order to figure out our protons and electrons. And so using magnesium as an example, if we were to zoom in, we have our atomic number is 12, so the atomic number is often thrown in the lower left corner, and that tells you in a neutral atom your number of protons and your number of electrons. So magnesium would have 12 protons and it would also have 12 electrons. If it became an ion and it lost some electrons, then those two would no longer be equal. But in this case, we're just saying for neutral magnesium. So you definitely want to be able to remember how to write electron configurations, how to use the periodic table to your benefit, and read specific things off of the periodic table that will be useful. When we are talking about chemical bonding, whether we're talking about forming an ionic bond or a covalent bond, we are usually referring to something called the octet rule, meaning that your atoms will either gain or lose electrons, or they will share electrons in order to obtain noble gas configuration, meaning they have 8 electrons shared between them. So that is the octet rule. That's where they are stable. Noble gases particularly don't react because they have a full valence shell. So they are happy. The other way you can predict the number of valence electrons a representative element will have, which representative elements, those are going to be your first 2 columns and your last 6 columns, is you can look at the group number. So if you're in group 1A, the number of valence electrons in that group, every one of them has 1 valence electron. In group 2A, all of those have 2 valence electrons. And then we move over to the right side of the periodic table, skipping over those transition metals. You have 3A, 4A, 5A, 6A, 7A, and then the noble gases 8A. So with the exception of helium, all of your noble gases already have 8 valence electrons, which makes them stable. So you can quickly look at that group number for a representative element to determine the number of valence electrons without actually writing out the electron configuration each time. All right, first let's review ionic bonding. When you have an ionic bond, you basically have an electrostatic interaction between a cation, which is a positively charged ion, and an anion, which is a negatively charged ion. And so plus and minus attract one another, so positive and negative charges will be attracted, whereas like charges would repel. And since we have opposite charges, they're going to have some degree of pull towards one another, and that amount of pull is essentially what an ionic bond is. And so ionic bonds are formed between a metal that becomes a cation and a nonmetal that becomes an anion. So our metal species will lose electrons to become a cation, and our nonmetal species will gain electrons to become an anion. And they're still going to follow that octet rule when they come together to form that ionic bond. So for example, if we look at the crystal salt structure of something like potassium chloride, which is KCl, we can write the shorthand electron configuration for potassium, which if we look at the periodic table, the preceding noble gas is argon, and then we're going to have 4s1. So the number of valence electrons in a potassium atom, a neutral one, is 1. It's in group 1a, and it has 1 electron in its outermost 4s shell. So if it gives up that 1 electron and becomes the potassium plus 1 ion, its valence electron is going to essentially be the same as argon. It will be the same as argon. Those two are called isoelectronic because they would have the exact same electron configuration. So in that case, it gave up its valence electrons. So we'll say that it now has 0 valence electrons. And we can do the same thing for chlorine. Chlorine's shorthand electron configuration would be neon brackets, and then we're going to have 3s2, 3p5. So notice that chlorine now has 7 valence electrons. It has 2 in the 3s and 5 in the 3p. And you could also look at the periodic table and see that it's in group 7a. So group 7, 7 valence electrons. So chlorine will need 1 more electron, and it'll be easier for it to accept that electron in order to have 8 than it would be to lose all 7 of them. Whereas for potassium, it's easier for it to give up 1 electron than it is for it to gain 7. So when chlorine becomes the chloride anion and it gains a negative charge, it'll gain 1 electron, and its electron configuration will be neon, brackets, 3s2, 3p6, which that's technically the same as argon. So those are isoelectronic as well. And now it would have 8 valence electrons total. So it will have achieved an octet. So there's a transfer of electrons from potassium to chlorine to form a potassium cation and a chloride anion. And those two are held together by that electrostatic bond. And each different solid ionic compound that you form could have a bit of a different crystal structure. So what you're looking at over on the right hand side is the crystal structure for sodium chloride. And in each one of them, so each chloride anion, which is the larger red spheres, those are going to be surrounded by 6 positive potassium ions, and each blue positive sphere, so that's a potassium ion there, those are going to be surrounded by 6 chloride anions. And so this is actually the same crystal structure that sodium chloride or table salt would form as well. And there's all types of different arrangements and how many ions are surrounded by different ones and how they pack themselves and arrange themselves in the crystal structure. So that's ionic bonding. And you're going to want to understand essentially what it occurs between a metal and a nonmetal and how those electrons are transferred between them and what holds them together in an ionic bond is that difference in charges. So let's try an example, reviewing how many valence electrons are found in each of the following species. And using the periodic table is probably the quickest way to get at the number of valence electrons. So looking at a sodium atom, sodium is in group 1A, so number of valence electrons will be 1. A calcium atom, calcium is in group 2A, and so the number of valence electrons there is 2. Next we have oxygen, but notice it has a -2 charge, so O2 minus. That means that oxygen has picked up 2 extra electrons. So oxygen is over here, and it's in group 6A. So a neutral oxygen atom would have 6 valence electrons, but it's picked up 2 more, so we're going to add 2 to that number. So that would have 8 valence electrons. And lastly, we have Br plus. So that plus charge means that bromine has lost one of its valence electrons. So bromine is over to the right-hand side in group 7A. So a neutral bromine atom would have 7 valence electrons, but we're going to subtract off 1 because it has a positive charge, which leaves us with 6 valence electrons in a Br plus ion. So we said that ionic bonding is between a metal and a nonmetal, whereas covalent bonds, those are going to be formed by electrons being shared between 2 nonmetals together. In an ionic bond, we had a transfer of electrons from the metal to the nonmetal, but when we're dealing with covalent bonding, which is what we'll be looking at like 90% of the time, there are going to be electrons that are shared between 2 nonmetals. So if we imagine how a covalent bond forms, let's think about H2, which is hydrogen gas. And if we think about having a hydrogen atom with its 1 electron separate from another hydrogen atom with its 1 electron, eventually those 2 hydrogen atoms are going to have to approach each other along an imaginary internuclear axis. And when they do, there's a couple things that happen. There's some attractive and some repulsive forces at play that will determine when the system reaches an energy minimum and that covalent bond is formed. So there's repulsive forces between the electrons of both of them. There's repulsive forces between the nuclei of both of the hydrogen atoms, but there's attractive forces between the electron of one atom and the nuclei of another. So essentially it's a function of the internuclear distance. When they're really, really far away, there's no bond. And when it reaches that energy minimum, you'll notice that the energy is written as a negative number. What that negative number really means is that the system is now at an energy minimum where those electrons were able to move around in a way that they minimized their repulsive forces and they maximized their attractive forces. And so that's what gives us that net lowering energy. Where we are at that energy minimum, you can see that 0.74 angstroms. Angstrom is that A with the circle over top. That is a unit used to represent the bond length. So that's actually the bond length we would measure between the 2 hydrogen atoms at that lowest energy minimum. And if the hydrogen atoms were to come any closer, you can see that the energy is going to shoot right up and become unstable because at that point the repulsive forces are overwhelming the forces of attraction. So we're going to shoot up in energy. When we're talking about energies of systems, lowest energy is always what Mother Nature favors. It's always more favorable. So lower energy always means the same thing as more stable. And the opposite is true as well. If something is higher energy, that means that it's less stable. So that's why that would be considered our actual bond length at that lowest energy minimum. Another important concept to recall is electronegativity. Sometimes it's abbreviated as EN. And what that is the ability of an atom, when it's in a covalent bond, to pull electrons towards itself. You can think about the electrons sometimes being in kind of a tug of war between the 2 nonmetals that are in the covalent bond. And sometimes one atom is going to win that tug of war and pull those electrons closer in towards itself. Even though they're both technically still being shared, one of the atoms sometimes will win. And so The general trend for electronegativity when you're just looking at the periodic table and you don't know any actual electronegativity numbers is that it increases from left to right across a given period, and it also increases as you go from bottom to top within a given group or family. So it's important to know that general trend. You don't have to know these actual electronegativity values off the table. They can be useful sometimes, but if you know the general trend, you can figure out who is going to win that electron tug of war. All right, so if we use electronegativity to kind of compare two different covalent bonds to one another, we could draw a Lewis structure for H2, which that's fairly simple. We just saw it on a previous slide. Each hydrogen brings one valence electron to the dance, and so there is one covalent bond between each of the hydrogen atoms, and that covalent bond represents 2 electrons when we draw a line like that. And for HF, we would have hydrogen being bonded to fluorine, and our fluorine would have a complete octet, so it would have 3 lone pairs of electrons around it. Hydrogen follows the duet rule, so hydrogen is happy with only 2 electrons. And they think they own the ones that they're sharing within that covalent bond. Each of the atoms thinks that they own those 2. So if we compare these 2 Lewis structures, because the electronegativity of hydrogen, which that's kind of a floating element, it's over here, it has an electronegativity of 2.1. It's the same for both of the hydrogen atoms. So the difference in electronegativity, or delta En, would be 2.1 minus 2.1, which would be 0. This is an example of a nonpolar covalent bond. Nonpolar covalent bonds are usually pretty easy to identify. It's usually when you have 2 of the same atom bonded together. There's no one winning that tug of war, and the electrons between the 2 atoms are equally distributed because both atoms have the exact same electronegativity. Now, there are circumstances where you can have such a small difference in the electronegativity that it is essentially considered nonpolar covalent, even though you have 2 different atoms bonded together. As the difference in the electronegativity grows, then we're going to start seeing that we have something called polar covalent bonds, which is an example of what our HF is. So our electronegativity for hydrogen, we said, was 2.1. And fluorine is in the upper right corner. That's the most electronegative element on the table. So our electronegativity for fluorine is 4.0. And if we take the difference between those two and calculate our delta En, we would have our greater one, 4.0, minus our lesser one, 2.1, which gives us a delta En of 1.9. And the numbers themselves are, they don't really mean anything. There's some ranges that you can find that a certain, like about 0 to 0.5 means nonpolar covalent, and then between 0.5 and let's say like 1.8, some books say that means polar covalent bond, and then greater than that could mean an ionic bond. We're not going to really need to use those numbers for anything, but this is just showing you that the larger the difference in the electronegativity is between the 2 atoms, the more that stronger electronegativity atom is going to pull the electrons towards itself. So in this covalent bond, those 2 electrons are really close to fluorine. Fluorine is winning the tug of war because it's much more electronegative. And so what that causes is something called partial charges to develop. Polar covalent bonds compared to nonpolar covalent bonds have partial charges. And what that means is our fluorine, since it's winning that tug of war, it develops a partial negative charge. That is the lowercase symbol for delta. Kind of looks like an infinity sign on its side, and that means partial negative. Since fluorine has those electrons being pulled towards it, it has a little bit of a negative charge. And that leaves our hydrogen with a little bit of a partial positive charge because it's lacking some of those electrons being close to it in that covalent bond. So now these two electrons in our covalent bond are not equally shared, whereas they were equally shared on the left-hand side. So that is the major difference between nonpolar covalent bonds and polar covalent bonds. You want to be able to identify them, especially when we start looking at mechanisms and reactions and why reactions happen. They often occur because one atom has more electrons than another atom does. And knowing the distribution of electrons in much more complex molecules will be very important in the study of organic chemistry. So this slide is just showing you a rundown of kind of what we just talked about, the spectrum of polarity. So on the far left, you have your nonpolar covalent bonds, electrons being equally shared, no partial charges. In the middle, we have our polar covalent bonds, and in those, electrons are still shared because it's covalent, but they're unequally shared, which leads to those partial charges that we saw. So in this example, we have HCl, and so hydrogen developed a partial positive, chlorine developed a partial negative. And then the most polar type of bond would be the ionic bond, where we don't have partial charges anymore. We now have full charges that are the result of transfer of electrons. So sodium has a full positive charge. Chloride has a full negative charge. So the trend would be going from left to right that we are increasing in polarity as we go from nonpolar covalent to polar covalent all the way to ionic. Sometimes you'll see different various ways in order to represent the polarity of bonds. We saw that the electrons move away from the lower electronegativity atoms and they move towards the higher electronegativity atoms. So in this first example, if we had carbon and carbon bonded together, that would be an example of a nonpolar covalent bond where those electrons would be equally shared between the two of them. In our second example, if we have a carbon-oxygen bond, carbon and oxygen are going to have two different electronegativities, oxygen being more electronegative than carbon. So two ways that you could possibly see the polarity of the bond represented is using partial charges, which is what I typically use. So that delta plus and delta minus, which means partial positive, partial negative. Or you could see this arrow on the top, which is called a dipole arrow. And the dipole arrow represents the same thing as the partial charges. Notice the plus part of the arrow crosses at the carbon, which is the more electropositive atom, and it points towards the oxygen, which is the more electronegative atom. So it's showing you the direction of the dipole, or the polarity, in other words. Sometimes you'll have carbon bonded to a metal and it'll be kind of in between covalent and in between ionic in terms of the electronegativity difference. And so you can see with the dipole arrow, it's crossing at the lithium because that's a metal and it's going to be more electropositive. And it's pointing towards the carbon, which is the more electronegative between the two of them. And if the difference between the two of them gets high enough, sometimes they'll even represent them as if they're practically ionic bonds, showing that covalent bond breaking and those electrons going towards the carbon, which is why that carbon has a negative charge. And then the lithium has a positive charge because now it doesn't have those two electrons that were in that covalent bond. So sometimes both of those are used depending upon the reaction and the mechanism that we're looking at. And that's because polarity is essentially a sliding scale. There's really not a 100% ionic bond or really a 100% polar covalent bond. There is a sliding scale between them. We saw that as your difference in electronegativity, which is your delta En, increases, the more polar the bond gets. But you can have a lot of kind of in between. So nonpolar covalent bonds that are going to be important in organic chem are the carbon-carbon bond and the carbon-hydrogen bond. So carbon and hydrogen actually have a really, really close electronegativity, so their delta En is about 0. It's close. So essentially anytime you have a carbon-hydrogen bond, that is also nonpolar covalent. The nonpolar is often dropped because if it just says covalent, it's assumed to be nonpolar. Polar covalent is for sure always specified though. And so polar covalent bonds could kind of range from, we could have a nitrogen-hydrogen bond, we could have a carbon-oxygen bond, or that lithium-carbon bond, for example. But this is kind of a sliding scale in this range. Some of these at the far right end could be considered a little bit more ionic because you technically do have a metal-non-metal bond. Lithium is a metal, carbon is a non-metal. Same thing with lithium nitrogen, metal, and nitrogen is a non-metal. So technically by our definition we would call those ionic, but they fall in between that polar, covalent, and ionic according to their delta EM. And then something like sodium chloride is super ionic and it has very little polar covalency to it because it has such a big difference in electronegativity. They're on far opposite sides of the periodic table, far left and far right. But just remember, there's no usually 100% ionic or 100% polar covalent. They all have a range they kind of fall between.